So just to recap from last time, we talked a great deal about pressure, and we have a little bit more to talk about relating to pressure today to finish up this note packet, and then we'll start with the next one. So let's just dive in, and then it's not in the note packet, but I do have a fun demonstration and problem to do relating to pressure. It's one of my favorite things to do in class of all time. So I'm excited. So that's going to happen today. Okay. So we're going to start off today talking about barometers. A barometer is a device used to measure atmospheric pressure. And so what we have here is a little cartoon of a barometer. And so essentially what we want to do is a force balance on this column of water. All right, so this is just a recreation of the water that is right here. Right? All right, and then I also want to make note that this is evacuated at the top of this container. So we're assuming that there's a vacuum here. There's no pressure at the top of the water in this column. All right, so it's kind of already drawn here on this picture. We have on this column of water an applied force due to the atmospheric pressure. So the force here is P atmosphere times A. So this is our cross-sectional area. And the reason that we can say that this is atmospheric pressure is because we have atmospheric pressure at the surface of this water in our dish. And then at the same height through the same liquid, we get to the pressure at the bottom of this column. So we know that the pressures must be equal. So we have atmospheric pressure at the bottom of this column. We have no force on the top because it's a vacuum. All right, and then we also have the weight of the column. So weight is just going to be density times the volume times G, or rho times AH times G. So our volume is just A times H. All right, and this column of water is not moving. So when we say that the sum of our forces is equal to mass times acceleration in the vertical direction, we know that that's 0. So the total forces sum to 0. So we have a positive P atmosphere times the area minus rho AHG. So this is our weight, negative because weight points down. And these are equal to 0. So we can solve for P atmosphere here by first canceling out area from both of these terms. It's not equal to 0, so we can divide through by it. And then we will move rho GH to the right-hand side. Okay. All right, so that is how a barometer works. It's also worth mentioning that pressures associated with manometers and barometers are measured in terms of that height of the column. So we are measuring in terms of the length L, or the height H, in millimeters of mercury, which is abbreviated millimeters dash HG. Or sometimes it's inches of mercury, inches of mercury is written in that way. Inches of water, which is IN-H2O, etc. So we're going to need to be careful if we're given pressure in terms of length like this to convert it into something like bars or PSI or KPA, for example. So just to show you how you might do that, we're going to do an example where we have a barometer reading is 750 millimeters of mercury. And then we're going to assume that mercury has a density of 13,529 kilograms per meter cubed. That's from a table in your book. And then the typical value of gravity. Then to calculate the atmospheric pressure in bars, what we would do is we have that pressure is equal to rho, and we're using mercury in this case, GH. So we have 13,529 kilograms per meter cubed times 9.81 meters per second squared times 750 millimeters of mercury, which is this is just millimeters, right? We've already included the information about mercury in our density. Okay, so that's how that gets factored in here. And now we need to do some conversions. So we have 1,000 millimeters in every meter. So that takes care of this unit of millimeters. We have 1 kilogram per meter, 1 kilogram times meter per second squared in each Newton. So that takes care of this kilogram and this meters per second squared. And then we also have, I need to move this over just a tad. Oops. We also have that 1 Pascal is 1 Newton per meter squared. So the Newtons cancel here, and then we have the meter squared. So 1 over 1 meter squared is just meters squared. And then we have over here 1 meter divided by meters cubed. So this together is also meters, 1 over meters squared. So these cancel. And then last but not least, we want this in bar. So we have that there are 10 to the 5th pascals for every bar. All right, so that gets rid of the pascals, and now our only remaining unit is bar. Does that make sense to everybody? Okay, cool. And so when you do this calculation, you get 0.995 bar. All right, so essentially we need to use that equation that we derived here with the force balance that the atmospheric pressure is rho GH. Anytime you're given pressure in terms of a length, you're just getting H and some information about what density to use. Okay. All right, cool. Okay, let's do another example. So we have a frictionless piston cylinder device. So essentially this is just a cylinder with a disc inside of it. We're going to assume that the disc doesn't have any friction with the walls of our cylinder. And it contains a gas at equilibrium, and we want to find the equilibrium pressure of the gas. All right, so we are given information here. So we have that the atmospheric pressure above this cylinder is 0.97 bar. We know the mass of the cylinder is 60 kilograms. And the area of the cylinder is 0.04 meters squared. And we want to find P. Any ideas about how we should start this problem? No thoughts? Yeah. Yes, I love it. Remind me your name again? Wade, great. Yes, so we're gonna do a free body diagram for our piston. All right, and we're gonna draw the forces that are on it. So what forces do I have on this guy? Sorry? Yeah, so we have the force of the atmospheric pressure. Thank you, Mark. So this is going to be P atmosphere times the area. That's how we turn or translate our pressure into a force, pressure times area. We've got a pressure on the bottom side too, right? So we're going to have a pressure pointing up, which is the P we're looking for times A. Anything else? Yeah, we have our body force due to gravity, right? Is it Sophia? Yes. All right, I'm learning. Okay. So we're going to have our M times G, our body force pointing down. Okay. So what we want to do is we want to do sum of the forces in the Z direction is equal to mass times acceleration in the Z direction of our body. But we are told in the problem that this system is at equilibrium. What does that mean about A? Yeah, so it's equals to 0 because it's in equilibrium. All right, so we can say that the sum of the forces has to be 0. So I'm just going to add up these forces that we've done on our free body diagram. So we have a positive pressure times area, a negative P atmosphere times area, and then a negative mass times gravity is equal to 0. All right. I'm going to divide this through by A, and then I'm going to move the P atmosphere and the mg term over to the right-hand side. So I'm going to solve this thing for P. So we have that P is equal to P atmosphere plus mg divided by A. Right? And we have all of these things, right? So we have P atmosphere, we have M, we know G, and then we also have A. All right, so we can just plug in our values that we have and solve this problem. So let's do that. So we have P is 0.97 bar plus M, which is 60 kilograms, times G, 9.81 meters per second squared, divided by 0.04 meters squared. And then I need to convert this into units for bar because I'm adding with bar in our first term in this equation, right? Units have to be the same in order to add them. So let's do that conversion. So the first thing we're going to convert is we're going to say 1 kilogram per meter times meter per second squared is a Newton. And 1 Newton per meter squared is a Pascal. And 1 bar is 10 to the 5 pascals. Okay. So our kilogram cancels out here. Our meter per second squared cancels out. Our Newton cancels out here. And then 1 over meter squared cancels with 1 over meter squared. And Pascal and Pascal cancel out, and all we have left is 0.97 bar plus whatever this works out to be bar, right? And so we get 1.2 bar. Any questions on that one? Okay, as a second part of this question, what if we heated up the gas and the piston rises? What do you think the new equilibrium pressure is going to be like compared to the first one we calculated? So if we go from this to this by adding heat. What's the difference between P1 and P2? What do we think? In your mind, think about repeating the same process that we did already. What would change for the second circumstance? Anything? Nothing, right? So our pressure is exactly the same. Even though our piston has moved, the pressure is exactly the same. So at equilibrium, the pressure balances with P atmosphere and the weight of the cylinder. I'm sorry, of the piston. So the pressure stays the same. Or P1 equals P2. All right. Okay, so we talked a lot about barometers and manometers. There's other methods to measure pressure. They include different types of sensors that rely on diaphragms, for example, that will deflect, or piezoelectric elements that develop a voltage with an applied force. This is how strain gauge pressure transducers work, for example. So that is just an FYI sort of a thing. It'll likely come up, maybe not. It could come up in lab that we talk more about different types of sensors for measuring things like pressure. Okay, we're going to talk about temperature, but before we do that, I want to do a fun little problem / demonstration. Okay, so I have a Erlenmeyer flask of water right here. And I also have a playing card. So this is like, you know how they're waxy. I'm going to put it right on top. And the question is, what will happen if I flip this whole thing upside down? Okay, so essentially what we have is we have our flask of water. And this is all the way full to the brim of water. And then I have a playing card right here. So the question is, what does the card do? Any ideas? How would we puzzle this out? And we're going to assume that the density of water is 1,000 kilograms per meter cubed. We're going to assume the mass of the card is about a gram. It's probably less than that, but that's okay. And then we'll also assume that atmospheric pressure is 100 kPa. All right, so how would we figure out what will happen to the card? What should our first step be? Perhaps a free body diagram again. So let's draw a free body diagram first. For the card. All right, so what are the forces that we have on our card? We've got body force, yes, so gravity. So we have mass of our card times G. And just for simplicity, I'm going to call G 10 meters per second. I did not bring a calculator with me, so we're going to estimate, okay? Okay, what other forces do we have? Yeah, so we have pressure from our water. So we're gonna have pressure of the water times this area. And I'm gonna call this 1 centimeter squared, roughly. All right, and then we also have an opposing pressure from the bottom where we have P atmosphere times A, right? Okay, cool. So let's do our free body diagram in Z. We want to do this force balance for the instant that we remove our hand from holding this together. Oh, sorry, yes.
Would there be pressure from the atmosphere also going down, like on the sides that are outside of the?
I love this question. Yes. So pressure, this is a great question. So we have pressure all around the card, right? So we're going to have, I'm going to draw this in another spot for explanation. Actually, you know what? I'll draw it on the diagram. So we have atmospheric pressure, which always acts onto a body perpendicular to it, right? Just like this. So here's all of our P atmospheres. And we have it on the flask too, right? Although that doesn't matter as much because presumably we're holding the beaker, right? So you'll notice that we have equal and opposite pressures in a lot of places, right? So pressure from the atmosphere is equal and opposite, meaning it balances itself in a lot of places. Is that not legible? Hang on, I'll choose a different color. So in the highlighted regions, it's balancing itself, right? So it's balanced here and here, and it's balanced here and here, and then from side to side, right? But then we have this little segment at the bottom where it's not balanced, right? So that's the only atmospheric pressure that we actually have to concern ourselves with. You could write it down, but then you would just have P atmosphere minus P atmosphere for all the places that are not where it's in contact with the water. Excellent question. Does this make sense?
Yeah.
Cool. Okay, so we're gonna assume that we're gonna release our hand from the card, and in that instant, we wanna figure out what the force balance looks like. So in that instant where we've removed our card, we're gonna assume that it's not moving. So we're gonna say that AZ is equal to 0 initially. All right, and then let's look at our force balance. So we have minus pH2O times A minus M times G plus P atmosphere times A is equal to 0. You know, actually, I want to recast this a little bit. Okay, so taking a step back, we're looking at a force balance, and we know acceleration is going to happen depending on what our forces are. So how would the forces have to balance if the card were to stay supported or fall down? So we have our negative forces, and then we have positive forces, right? So we have our negative forces are pH2O plus M times G, right? That quantity is our force pointing down. And then our force pointing up is P atmosphere times A, right? So these are our negative ones. These are our positive ones. So what would happen if this were true? The card falls, right? And then what would happen if the opposite were true? Card stays. Okay, so the name of the game is we need to figure out which is the case, right? So let's do it. But first we need to know what is pH2O. I forgot an A on there. Sorry about that. How can we calculate pH2O? We have the tools to do this. So we usually do a reference pressure plus rho GH, right? Do we have a reference pressure in this case? What's the pressure at the top of that column of water? We don't have one, right? So there's only water in here. There's a solid surface all around it. We have no pressure at the top. So all we have is rho H2O, G times H. All right. Okay, so our negative forces are rho H2O GH plus mg. And then our positive forces is just P atmosphere times A. All right, so we have all the values to do this. So let's plug them in. So I have 1,000 kilograms per meter cubed times 10 meters per second squared times 10 centimeters. And I need to do some conversions here. So there are 100 centimeters in a meter, right? And then that will give me, I cancel out these centimeters, and then I end up with just this 1 meter at the bottom, and then these 2 meters go away, right? So that is this term. And we get 1,000 kilograms meters per second squared, meters per meter second squared. Hang on, I think this is, yes, okay. And then this m times g, oh, we need an area. That's why. So we need our area in here. That's why the units are not correct. So always check your units. All right, and then our area is, what did I say? 1 centimeter squared. So we have 1 centimeter squared, and then we're gonna multiply by 100 centimeters in each meter, and we have to square that, right? Bless you. All right, so we have 1,000 times 10 times 10 divided by 100 times 1 times 1 divided by 100 squared, right? Anybody tell me what this is? So this cancels, right? 1 over 10. Okay, and then our units are kilograms meters per second squared, right? Because we canceled out these centimeters squared, and then meters squared divided by meters is just meters. Okay? Okay, so this is our term in the purple. Is this And then our next term we want to do is m times g. So our mass is 1 gram times 10 meters per second squared. We need this to be in kilograms times meters per second squared. So we have 1,000 grams per 1 kilogram. So we get rid of our grams in favor of kilograms here. And now we have 1 over 100, right? Kilograms per meter per second squared. Okay, so our negative forces are 1 over 10 plus 1 over 100, or 0.11 kilogram meters per second squared. Does everybody agree? Okay, now let's talk about our positive forces. So we have P atmosphere times A, which is 100 kPa, times our area, which is, what did I say it was again? 1 centimeter squared? 1 centimeter squared. And we're going to need to convert this too. So first, let's do 1,000, or sorry, 1 kPa is 1,000 pascals, right? And 1 pascal is 1 kilogram meter per second squared, right? And then we need to convert our 100 centimeters per meter squared. Okay? So we cancel out our kPa, we get rid of pascals, and then you know what, I skipped a step, sorry. So we need to, this 1 pascal is a Newton per meter squared. Right? And then we have that 1 Newton is 1 kilogram times meter per second squared. Okay, now we can put in our centimeter conversion. So we have 100 centimeters per meter quantity squared. All right, so our centimeters squared cancel. And then we end up with 100 times 1,000 divided by 100 squared kilograms per meter per second squared. Because this meter squared and this meter squared cancel, and then the newtons go away too. Okay, so this is our remaining unit here. Okay, so what does this equal to? 10, I think. It's 10, right? Okay, so we have 10 kilograms meter per second squared. So what does that mean? What will happen? How is 0.11 kilograms per, or kilogram meter per second squared equal or related to 10 kilogram meter per second squared? Yeah, we have this, right? So the card should stay, right? Do we feel confident about it? Does anyone want to volunteer to have their friend do this above their head? You're going to do it to him, Mark? Or other way around? Yes. Okay, hang on. Are you going to do it? No pressure. You don't have to. The math is good. Okay. Do you want a chair? He's soft. He should have. Let's place it on him. It's just water, okay,
If
so,
you sell. Right, empty my pockets.
I mean,
It's not gonna fall, obviously. I'm not comforting you. I don't know. Your hands are sticky.
the math doesn't lie. Yeah, this, I'm getting you the flattest card. Here we go. This is a good one. All right, so. Totally full of water, yes. Here's the card.
Show me your hands.
So just hold it together, flip it upside down,
And let go of that card.
and then you can let go of the card.
I don't want to let go of the card. No.
Okay, no. If there's this, okay, so.
Not even one little bit of faith.
Great. Okay, so this is actually important. So as soon as the air gets inside of here, you have atmospheric pressure on the top of the water column, and this no longer works. So do you want to refill it?
Oh, yeah.
Okay.
Wait, can you do it? Oh, yeah. I'll sit in the chair.
Wait, it's only fair.
5 minutes later.
I'll give you a second try. No, I already I just emptied my pockets. There's air.
Okay, here, I have water.
That's you can do it. Okay. It's okay.
All right.
All right.
There's gonna be some drips regardless.
Isn't there still air bubbles? There's air bubbles.
There's still air bubbles?
Yeah.
Okay. Flip it back over, we'll add some more. That was to the top.
It does.
It seemed like it was to the top.
That was a good catch, guys.
I'm glad we're watching very carefully. That's good.
And that card's pretty wet.
It's okay. Oh, hey, there we go. Well done, thank you. So I love this kind of thought experiment and demonstration because I think generally we don't appreciate how much atmospheric pressure actually is. Water seems heavy to us, right? But atmospheric pressure is actually quite a lot. So thank you guys for your participation. Whoop. That was fun. So now we can talk about temperature, which is less fun than that. I'm sorry, it's all downhill from here, actually, for this lecture. That was peak fun, at least for me. Okay, all right. So this is a thermal engineering class. We're going to be talking about temperature a lot. So it's best to make sure that we can know the different units at our disposal and then how to convert between them. So that's what we're going to do here. So all of us are likely very familiar with the concept of temperature. It's a measure of hotness or coldness, of course. And we can perceive it qualitatively with our senses, right? The issue with only using our senses is that our senses can be misleading, right? So you could have a wooden chair and a metal chair at the exact same temperature. The metal chair is going to feel a lot colder to you via your senses than the wooden one. And so that's why it's important to have a quantitative measure that we can use instead. So we can measure temperature with a bunch of different types of devices, such as liquid in tube, or infrared thermometers, thermocouples, or thermistors. All right. The main idea with temperature is that when a hot body is brought into contact with a cold body, heat is going to be transferred from which body to which body? Hot to cold, right? We know this. So from the hot body to the cold body until thermal equilibrium. or I'm sorry, until both bodies have the same temperature. Which is just another way of saying that they're in thermal equilibrium. Okay, the 0th law of thermodynamics. So this is the first of the laws of thermodynamics that we are talking about in this class. And it states that if two bodies are in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. And so this idea serves as the basis of validity for temperature measurement. Because the third body would be the thermometer, for example, or the thermistor, or the thermocouple. All right. Okay, so let's talk about temperature scales. So temperature scales are generally defined by assigning a value at a standard fixed point. So they're generally defined by assigning a value at a standard fixed point. All right, for SI units, Celsius. Oops, Celsius. So this is degrees C. Freezing point of water at 1 atmosphere is 0 degrees Celsius. And then the boiling point of water at 1 atmosphere is, of course, 100 degrees C. And then these values are also defined in English units, which are Fahrenheit. Or degrees F. So the freezing point of water at 1 atmosphere is 32 degrees Fahrenheit. And then the boiling point of water at 1 atmosphere is 212 degrees Fahrenheit. All right. The Kelvin scale, which note there's no degree symbol in front of Kelvin, that's just Kelvin, is an absolute thermodynamic temperature scale. All right, so what we have is that the temperature in Kelvin is equal to the temperature in degrees C plus 273.15, or sometimes approximated as the temperature in C plus 273. Right? Hopefully we've all seen this before. Yeah? Okay, cool. Okay, so let's consider two temperatures. We're going to call them T1 and T2, and we're going to compare the difference between them in Kelvin and in degrees C. So essentially we want to know what is T1 in Kelvin minus T2 in Kelvin, and figure out how that's related to the temperature difference in degrees C. All right, so what I'm going to do is I'm just going to essentially rewrite this statement, but using this version of the definition for a temperature in Kelvin. Okay, so we have T1 in degrees C plus 273 So this is T1. All right. And then I also have minus T2 in degrees C plus 273. So this is just a restatement of T2 in Kelvin, right? What happens to the right-hand side? Does anything convenient happen here? Yeah, we got 273 minus 273. Thank you, Mark. They go away. So we just end up with T1 in degrees C minus T2 in degrees C. All right, so this means that our temperature difference is going to be identical if we measure the temperatures in Kelvin and compute the difference, or if we measure them in Celsius and compute the difference. Okay. Excellent. So just like kind of how Kelvin is related to Celsius, we have a similar absolute thermodynamic scale for English units called Rankine or degrees R. And so that conversion looks like this. So your temperature in degrees R is equal to the temperature in degrees Fahrenheit plus 459.67, or sometimes approximated as the temperature in degrees Fahrenheit plus 460. All right, so if we want to look at the T1 in degrees R minus T2 in degrees R, we're going to do the same thing, but now we just have a different factor in there. So we have T1 in degrees Fahrenheit plus 460 minus T2 in degrees Fahrenheit plus 460. So I've got my T2 just restated like so, and then T1 also restated but equivalent. And we have the 460 minus 460, just like how we had the 273 minus 273. So if we do a temperature difference using Rankine and then a temperature difference using Fahrenheit, we'll get the same difference between those two things again. So delta T in degrees R is equal to delta T in degrees F. All right. A very important conversion is the following. So if we have temperature in degrees Fahrenheit, or I'm sorry, if we have temperature in Celsius and we want to convert it to Fahrenheit, we take 1.8 times the temperature in degrees C and then add 32. Okay. And to kind of illustrate the challenges that this type of a conversion has, I have a little case study for you to look at. So you'll notice that when we were converting from Celsius to Kelvin or from Fahrenheit to Rankine, we just had an added factor on there, right? Now we have an added factor and a multiplicative factor. All right, so this is going to complicate things for us just a hair. All right, so I would like you to take a look at this statement in an article about climate change. And this has actually happened a number of times, but this is just one example of it. So the statement is that in the report Trajectories of the Earth System in the Anthropocene, published Monday in the American Proceedings of the National Academy of Sciences, it said hothouse temperatures could stabilize 4 degrees to 5 degrees C or 39 to 41 degrees Fahrenheit higher than pre-industrial levels. Do we see any issues? Just kind of as a sanity check, does that sound right? Okay, what issues do we see with this? Any off the bat? Anything that doesn't feel sensical to us? Yeah. Yeah, it's Leo, right? Okay. Yeah, so Leo is correct. So let's check their conversion, right? So they said that they took a change in temperature in degrees C, which is 4 degrees C. And this is T2 in degrees C minus T1 in degrees C. And then they also want to, compare that with a temperature change in Fahrenheit. So we have T2 in degrees Fahrenheit minus T1 in degrees Fahrenheit. All right, so let's actually do this conversion properly. So for T2, we would take 1.8 T2 in degrees C plus 32 minus 1.8 T1 in degrees C plus 32. All right, so since we're looking at a temperature change, we have this cancellation of 32 minus 32 that happens, right? So we should just have 1.8 times the quantity of T2 in degrees C minus T1 in degrees C. All right, so if we did this, we should get 1.8 times 4 degrees C is equal to 7.2 degrees Fahrenheit. And then at the upper end, for a 5 degree C delta T, we would have 1.8 times 5 degrees C is equal to 9 degrees Fahrenheit. Okay, so they didn't account for the factor of 32 canceling. For a change in temperature. Does that make sense? All right, so when you're converting from temperatures from Celsius to Fahrenheit or vice versa, you just have to be careful of things like this. Okay? Okay, cool. This is the end of our first note packet and probably a good time for a break. So let's take a break and then I'll get the next packet loaded in. Good work with the demo. Thank you. Yeah.
So I was looking on the Moodle for like the Lab Zero assignment that you had mentioned.
Yeah.
And I see it,
Oh, it'll only be in our lecture section.
okay, yeah, so I see that here.
Yeah.
Then in the lab session one, there's 2 other assignments.
Oh, you know what? I need to fix that.
Those
Those
two.
are just references that I accidentally uploaded as assignment format. They're just
Okay,
files.
so nothing needs to be.
No.
Okay.
No,
I'm
I'll
trying to
fix
look
that
at
after
it like
class.
right from this here.
Yeah, I'm sorry. That was my fault. No. I wouldn't do that to you. Sorry about that. That is confusing. I wonder, I'm gonna have to do it on my laptop.
Yeah. Yeah.
Yeah.
And then there was one of them, there's some of the albums, it's got 16 albums.
Yeah.
This morning, and I was looking at Google and I saw like the only things that were like for submission was just the notes. that we
Oh,
took.
yes.
Is there anything else?
So, okay, I need to, in the lab, Moodle page, there will never be assignments in there. So like I uploaded files as assignments on accident.
Okay.
I'll fix that. So there's nothing actually due on the lab page. The lab zero assignment is in like the lecture.
Okay, perfect.
Yeah, so like
Okay, good
everything
to
that
know.
you do for the class comes through the lecture section because I grade
Okay.
it all.
Yeah, yeah.
Yeah,
that
since
would
like
be
anybody can sign up for the labs, it gets.
Yeah. Okay, I was like,
Sorry about that.
just in the
No, no. Yeah. That's, I'll fix it after class. I totally, yeah,
Okay.
was moving too quickly. Yeah. I'm gonna make an announcement about the assignment confusion after break. After everybody's here, I'll say it. I'm sorry, unnecessary confusion.
I remember I asked her for, I just wanted to, oh, what do I have? This is like, no. You got like, you study. Basically, yeah. A lot of it is just like, how you get to go beyond. You have into the.
Hi, question?
Yeah.
Oh, okay, yeah, welcome. You just got in, right?
Yes.
Okay, awesome.
I was wondering what I should do. I put my name on.
Oh, okay, perfect. I will assign you to a team.
Okay.
So I was just waiting until like today to give people a chance to sort of
Yeah.
equalize their teams. So I'll go in there tonight and put all the free agents in a place.
Okay.
Does that sound good?
Yeah. Thank you.
Awesome. Okay, cool. Okay. I'm gonna make a quick announcement before we start this next note packet, because I made something unintentionally confusing in Moodle, and I've gotten a couple of questions about it. I'm gonna fix this after class, but on the Moodle page for lab, it looks like there's 2 assignments in there. I just uploaded references as assignments on accident. So those are just files. They're not assignments. The Lab 0 assignment is on our lecture Moodle page. So everything that you turn in for this class will always be on the lecture Moodle page, just because of how we've structured the lab sections and the lecture sections independently, if that makes sense. So I'll fix that tonight. So do not panic. There are not 3 things due for lab 0. And then, oh, I also wanted to mention, I'm going to post hopefully tonight, but if not tonight, tomorrow, I'm going to have homework 1 will cover all the stuff in that note packet that we just finished. And I'll put that on Moodle. And I think I need to shift the due date in the schedule. I'll always give you at least a full week to work on a homework assignment. Okay. Okay, cool. Any questions on the last note packet before we move on? Okay, perfect. Okay, so in this topic, we're going to be talking about energy and energy transfer. So we previously defined thermodynamics, very first day of class, as the science of energy. So energy, which should not be surprising, is one of the most fundamental concepts of thermodynamics. Okay, so you all probably know this already, at least to a degree, that energy can exist in several different forms. What types of forms are you used to seeing energy in? Can anybody think of any? Leo. Oh, I'm thinking even like more basic than this. So like in like high school physics, for example, you talked about probably kinetic energy. Yeah, potential energy. I think some of the examples you rattled off there might have fallen into the chemical energy category, if I recall. Energy, electromagnetic, electrical, nuclear, thermal, and so on and so forth. Okay. The sum of all the energy that exists within a system is called the total energy. And we generally call this E. All right. The units for energy is 1 joule in SI, or it's abbreviated J. We also use BTUs, or feet times pounds of force. It's also important to note the conversion for joule. So 1 joule is equal to 1 Newton meter. Sometimes you'll see like a period between these two. That just means they're multiplied together, in case you're curious. Okay. And then we also have a conversion for BTUs. So 1 BTU is 778.17 feet times pounds of force. Okay. We also have specific total energy. So just like when we talked about specific measurements in the last unit, we're dividing by mass. And specific energy is going to have a lowercase e. So that's our convention that we've been using. So we have the total energy divided by m. So we have total energy divided by the mass of the system. This is going to have units of kilojoules per kilogram or BTU per pounds of mass. Okay. Thermodynamics is generally only concerned with change in total energy. So that means that typically what we're going to do is we're going to assign a value of 0 to the total energy at some convenient reference point, and then we'll measure changes off of that. This is very similar to like what you did probably a long time ago when you started looking at potential energy and you decided some reference point is going to be my Z equals 0. And therefore the potential energy at that point is also 0. Okay, so it's the same idea. Okay. So all of these types of energy can be classified into two categories. We have macroscopic. So these are forms of energy that a system possesses as a whole with respect to some outside reference frame. They're related to motion and other external factors like gravity, magnetism, electricity, and surface tension. All right, so some examples of this include kinetic energy, which we all know and love is 1/2 mv squared, where m is the mass, v is the velocity. Specific kinetic energy is equal to 1/2 v squared, right? So we just divide kinetic energy by mass. Another example of this is potential energy. Which we all know is mgz. So this is elevation relative to a reference point. And then we have mass and gravity, of course. Our specific potential energy is just G times Z. Right? So these are both macroscopic types of energy because they depend on an external reference frame. So the velocity is kind of our reference to an external reference frame, and then obviously gravity for the case of potential energy. When we're dealing with kinetic and potential energy in the SI system, we need to be careful about units. So for example, if we wanted to calculate the kinetic energy plus the potential energy in kilojoules, given that we have a mass of 1 kilogram moving at a velocity of 10 meters per second at a relative elevation of 1 meter, and given that gravity is 10 meters per second, let's do this calculation and just see what happens. So we have kinetic energy plus potential energy is 1/2 mv squared plus mgz. All right, so we have 1/2 m is 1 kilogram times velocity, which is 10 meters per second, that whole thing squared, plus m, which is 1 kilogram again, times 10 meters per second squared, times z, which is 1 meter. This is a 1. All right, so we have then $60 kilograms meters squared per second squared. So if I do this computation, our units are kilograms times meters squared per second squared, right? And we want to convert this into kilojoules. So we have, bless you, 1 kilogram per meter times meters per second squared is a Newton. Oops. Right, so this takes care of the kilogram. And then we are left over with 1 meter, right? And then we need the conversion that 1 Newton meter is equal to a joule. So this balances the newtons. And then we also take care of this last meter that was left over. And then finally, we want to convert to kilojoules. So I have 1,000 joules in a kilojoule. There we go. All right, so this is equal to 0.06 kilojoules. Okay. So essentially what's happened here is when we had the units in kilograms, meters squared per second squared, that is joules, not kilojoules yet. Okay, so just be careful with that. It can be a little bit tricky. All right. So, okay, yeah, this is the note that I just wrote here. So essentially, if you're in SI units, if you want kilojoules in the end, then you're going to have to divide through by a factor of 1,000. Okay. Okay. So that's macroscopic. We also have microscopic forms of energy. So these are related to the molecular structure of a system. And its molecular activity independent of an outside reference frame. So this is this includes things like sensible energy, which is essentially the kinetic energy of molecules, including translational, rotational, and vibrational kinetic energy of those individual molecules. We also have latent energy, which is the energy associated with intermolecular forces. So this is dependent upon the phase, whether it's solid, liquid, or gas of that material in the system. It also includes chemical energy. All right, so energy is associated with atomic bonds between molecules, and then this energy obviously can change during chemical reactions. And then last, we have nuclear energy. So this is associated with the bonds between the nucleus of an atom and its electrons. So this energy is released during during nuclear reactions. Okay. The sum of all the microscopic forms of energy of a system is called the internal energy of the system. And this is assigned the variable U, capital U. So specific internal energy is a lowercase u, which is why I'm writing the uppercase U in such an obnoxious way, because it's hard to distinguish U's that are capital and not capital in handwriting. So that's how I do it. So we have our total internal energy divided by the mass. And the units here are kilojoules per kilogram or BTU per pounds of mass, just like before, because this is still an energy. So our units are still going to be the same. In this class, we're generally going to neglect magnetic, electric, and surface tension effects. So if we get rid of those things and assume they're negligible, then we can express the total energy of a system as the following. So our total energy of our system is the total internal energy, U, plus kinetic energy, plus potential energy, which we can write as U plus 1/2 mv squared plus mgz, or mass times the specific internal energy plus 1/2 mv squared plus mgz. The specific total energy is basically just this equation, and we're going to divide through by m. So we have E is equal to U plus 1/2 v squared plus g times z. Okay. So energy can be transferred in different types of modes. So a system can gain or lose energy across its boundaries during a process. So a process takes us from one state to another state, if you recall. There's three basic modes of transferring energy. The first one is heat transfer. We give this the symbol Q. So this is energy transfer by virtue of a temperature difference. So if the temperature changes, we're transferring energy. We can also transfer energy through work. Symbol is W. So this is energy transfer due to a force acting over a distance. And then last is mass flow. And we're going to call this E with a subscript mass. So in the case of an open system, so if you have a control volume, if you recall, energy can flow in and out, and so can mass, right? So the energy of an open system can then be changed by adding or removing mass from it, because the mass is going to carry its own total energy. So as the mass comes in or leaves, then you're going to change the total balance of energy in that system. Does that make sense? Okay, so this is for open systems only. And that's because closed systems can't have mass coming in or out. All right. Okay, so just to draw a picture for a closed system, what we have is, if you imagine a rigid box, and then we have heat that could come in or out, and we have work that could come in or out. But that's it. We have two modalities of energy transfer for a closed system. If we have an open system, then that means that we can have mass in as well as mass out. And then this would be E mass in and E mass out. And then we still have the opportunity for heat and work in this system. All right, so for our three modalities, you can have heat transfer with both open and closed systems. You can have work for open and closed systems. But the mass flow transfer of energy can only happen for an open system. Okay? Any questions on that? Cool. Okay, so we are going to now begin with a preliminary statement of conservation of energy. So this is the first law of thermodynamics, and it states that the energy can neither be created or destroyed. It can only change forms. Meaning it can go from one type of energy to another. So you can transfer from potential energy to kinetic energy, but the total amount of energy that you have must stay the same. All right. So that means that every single bit of energy in our system has to be accounted for during a process. All right. And we can write that down as the following. So we can say the net change in total energy within our system is equal to the energy added to the system. So this is the energy coming in. minus the energy removed from the system or the energy going out. All right. All right, so if we have a process that goes from an initial state that we call 1 to a final state that we're going to call 2, we can write the following expression. So we can say E2 minus E1 is equal to E in minus E out. All right, and we can expand this because we know there's 3 different modalities for energy transfer. So we can have E2 minus E1 is equal to Q in plus W in plus E mass in. All right, so this is E in, which we've broken down into the 3 different modalities, minus Q out plus W out plus E mass out. All right, so that is just the breakdown of E out in the 3 different ways that energy can go out. All right, in the textbook, they'll also make reference of E in minus E out is equal to delta E of the system. So that is terminology in the book, just so you're aware how it relates to what I'm writing in the notes. Okay, so let's do an example. We've got an example about cooling of a hot fluid in a tank. All right, so we have a closed system of mass 2 kilograms that initially has a specific internal energy of 100 kilojoules per kilogram. It undergoes a process during which there is energy transferred by work to the system of 10 kilojoules, heat loss of 100 kilojoules, an elevation decrease of 10 meters, and an increase in velocity from 5 meters per second to 15 meters per second. We want to determine the final internal energy of the system. All right. So let's do a picture. So we are given that we have a mass. All right, and then this is my system boundary. It's going to include the mass. And since it is a mass and our system just includes the mass, what type of a system do we have? Open or closed? Closed. Yep. So this is a closed system. And then we're given some information about this. We're given that M is 2 kilograms. We're given that its initial specific internal energy, so my lowercase u at state 1 is equal to 100 kilojoules per kilogram. We have energy transfer by work to the system. So we have a W in is equal to 10 kilojoules. We have heat loss. So this is Q out of 100 kilojoules. And we have an elevation decrease. So Z2 minus Z1 is equal to minus 10 meters, right? And then we have an increase in velocity from 5 meters per second to 15 meters per second. So V1 is 5 meters per second, and then V2 is 15 meters per second. And what we want to find is the final internal energy of the system. So we want to find capital U2, right? Okay, so just to draw a picture for this, we have work coming in we have Q coming out. We have a change of velocity, which is a little bit challenging to draw here, but then we also have a change in the vertical displacement of this thing. Okay. Okay, so our governing equation that we're going to use is conservation of energy. So our governing equation is conservation of energy, which is E2 minus E1 is equal to E in minus E out. All right, so we're going to have to expand each of these terms. So our total energy, we already know, is a sum of internal energy plus kinetic plus potential energy. So we're going to have to write down those three types of energy for state 2 and state 1. All right, so we have U2 plus 1/2 mv2 squared plus mgz2. So this is E2. And then we're going to subtract off E1. So it's basically a restatement of these three terms again, but at state 1. So we have U1 plus 1/2 mv1 squared plus mgz1. So here's E1. And that is equal to E in, which is Q in plus W in. I am not doing E mass because this is a closed system, right? So we don't have it. So this is our E in. And then we have minus Q out plus W out. All right, can we simplify anything in here? Is there anything that we don't have in this problem that we can get rid of? Right off the bat. Yeah, so we don't have a Q in and we don't have a W out. So we can get rid of those right off the bat. All right. And then everything else, let's see what else let's see if we're missing anything. Okay, so we want to find this. So I'm just going to circle it here so we know to be on the lookout. So that's fine. We're going to want to isolate that. And then we are given M. So that's good. We have that. We're given V2 and V1. We know what gravity is. And we're also given U1 because we're given specific U1. And that is just U1 times M. So that's given, right? And then we kind of have these two because we're given Z2 minus Z1. All right, so we're going to have to do a little bit of work to get that into a form that we can use, but we're given it in some form, okay? And we also know the value of W in and Q out. All right, so we have everything that we need, and we just need to kind of algebraically manipulate this to get our Z2 minus Z1, and then isolate U2 on the left-hand side. Okay, so what I'm going to do first is I am going to solve for U2. So I have U2 is equal to U1 plus 1/2 mv1 squared plus mgz1 minus mgz2 minus 1/2 mv2 squared plus W in minus Q out. That feel good for everybody? Cool. I'm also going to make a note here. I wrote these next to each other on purpose, so I can rewrite this as mg z1 minus z2 or minus mg z2 minus z1. Okay. Okay, so let's start plugging in the information that we have. So we have U2 is equal to U1, which is our specific energy, 100 kilojoules per kilogram, times our mass, which is 2 kilograms, plus 1/2 2 kilograms times our velocity, which is 5 meters per second, squared, plus 2 kilograms times 9.81 meters per second squared. Z1 minus Z2. So we're given Z2 minus Z1 is minus 10. So that means Z1 minus Z2 is 10, right? All right, so I've got 10 meters. And then minus 1/2 2 kilograms times, I think it's 15. Yeah, 15 meters per second squared. Plus our W in is 10 kilojoules. And then our Q out is 100 kilojoules. Okay, so let's have a look at units before we go, wild with just adding and summing and multiplying and all this stuff. So we have kilojoules for this first term here, so that's good. So this is kilojoules. We have kilojoules here and here. But for these other three terms, if you remember, kilograms, meters squared per second squared, this is joules, right? Okay, so because of that, we need to divide each of these by 1,000. Does that make sense for everybody? Okay, great. This is a good example of why you need to be careful with the units, because it's very easy to just look at the kilograms, meters squared per second squared, and then add it to a kilojoule, but it's not the same. Okay, so when we do that, we get 110 kilojoules for U2, which is less than the initial energy, which was the 100, where is it? Kilojoules per kilogram times 2 kilograms, 200 kilojoules. All right, so our internal energy has decreased from state 1. Does that feel okay for everybody? More or less? A good time had by all?